Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With 200 gigabit private networking, scalable shared block storage, node balancers, and a 40 gigabit public network, all controlled by a brand new API, you get everything you need to scale up. And for your tasks that need fast computation, such as training machine learning models or building your CI pipeline, they just launched dedicated CPU instances. Go to pythonpodcast.com/linode, that's Linode today to get a $20 credit and launch a new server in under a minute. And don't forget to thank them for their continued support of this show. And you listen to this show to learn and stay up to date with the ways that Python is being used, including the latest in machine learning and data analysis. For even more opportunities to meet, listen, and learn from your peers, you don't want to miss out on this year's conference season. We have partnered with organizations such as O'Reilly Media, Dataversity, and the Open Data Science Conference. Go to pythonpodcast.com/conferences to learn more and take advantage of our partner discounts when you register. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the newsletter, and read the show notes. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers. Your host, as usual, is Tobias Macy, and today I'm interviewing Thomas Wiecki about PIMC3, a project for probabilistic programming in Python. So, Thomas, could you start by introducing yourself?
Sure, yeah. So I'm Thomas Wiecki. I currently work at Quantopian, which is a Boston-based startup in the financial space, and I'm the VP of data science there. Before, I did my undergrad in computer science at the University of Tübingen and then did my PhD at Brown University.
And do you remember how you first got introduced to Python?
Yeah, certainly. So when I was still an undergrad, I spent a summer at MIT doing brain stuff, and particularly we were training rats to do like certain experiments, and it's particularly the rats I was training to like do like a discrimination task that required me to lock myself into a dark room in the middle of the summer and just train these rats basically. So that felt like a really long time, these 2 hours, but it left me a lot of other time to explore other things. And that there I started using Python. Before I was like a MATLAB user, like a lot of the field back then. So that was early 2000. And what I liked about MATLAB was that it really allowed you to very easily like do numerical processing, have access to matrices and all these things. But it really didn't feel like a proper programming language. Like, so building actual packages out of that was really a hassle. And so Python, I immediately fell in love with because it was just as easy to work like from the Python shell, the IPython shell, and then create plots, and you had NumPy and SciPy and all these other things that could get you to parity with MATLAB, but also be an actual programming language to build packages. So that was really, we really dove into that because they had really time to dedicate to it. So at the end of the summer, while those rats never learned what I tried to teach them, I came out of that being a pretty good Python programmer.
And so the PIMC3 package says that it is usable for probabilistic programming. So can you start by explaining a bit about what that means?
Sure, yeah. So as the name suggests, it is about probabilistic models. And these probabilistic models you specify in computer code. And that already like makes me really like it because it allows someone with a computer science background to really dive into statistics. So I guess I should just talk a little bit more about like what probabilistic models are. So basically a probabilistic model is something that is made up out of probability distributions. So probabilistic programming allows you to do that quite easily, where you just have a whole bunch of probability distributions that represent how your problem is structured, and then you plug those together. And that is the common way that you do that, right? You plug probability distributions together, that is statistics, and then you do a whole bunch of math derivations to get at your estimator. Now, because we here are in code, not math, we can just write a line representing this is normal distribution and it's the input to another normal distribution, and then the computer figures out all the math for us. So we don't have to stand in front of a whiteboard. We are inside of a Jupyter notebook and just write down the model that we want. The other really important aspect is that the type of models we're building are generative. Yes, so it allows us to plug these probability distributions together in computer code and not in math. And also, these types of models are generative. So that means we think about the causes of our problem, and often these are unobserved. And then we think of how these causes generate the data that we end up observing. So one example for that would be A/B tests, which are very common in if you're building websites, right? You want to know which of those two websites, say, has a higher conversion rate. Maybe you want people to sign up to your website, so you have two different versions, and you want to say which one has a higher conversion rate. So at the core, that's a statistical problem, and you could use frequentist statistics. But in here, we're going to use Bayesian statistics. And the way to think about this in a generative framework is, well, we have these two unknown, unobservable causes, which produce our data. And these unknown causes are the conversion rates. And these produce either a user to sign up or not sign up. And these conversion rates, which we can't observe, because we're in a Bayesian framework here, we have to place priors on them. And that's a technical term from Bayesian statistics. And what it means is we define a probability distribution without having seen the data of what we believe likely values of the parameters to be. So in this case, we could say, I know ahead of time, right? If you're working in the web space, you know that conversion rates tend to be extremely low. I don't do that myself, but I know that it's less than 1% or in that area, but definitely not, say, 20%. So the probability distribution that I would build would place a lot of probability mass on really low values, because I know ahead of time that is going to be likely, but something like 50%, while not completely impossible, is going to be have a very low probability. And there's definitely some leeway in how you can define these priors, and maybe you're not an expert, so you could place wider priors on that, or you could ask an expert to provide you with that insight. So, okay, now we have defined our two conversion rates. And one more thing on the priors is we also, because it's a conversion rate, it's essentially a probability, so it has to be between 0 and 1, or 100%. And the distribution that is commonly used for that is the beta distribution. So that's just the name of that. And we can define these parameters of the beta distribution to give that lot of probability mass to very low probability values. And then we have to link that to observed data. So we say, okay, from these unobserved cases, we generate data that we observe. And in our case, these will be binary events, right? Someone did sign up or they didn't sign up. And the probability distribution, the likelihood function for that is called the Bernoulli or coin flip distribution. So that basically defines our model. So we have our beta distributions as priors for our unobserved conversion rates. And then we have our likelihood function, how my data is distributed, Bernoulli. So now, so far, I haven't seen any data yet. So that is just a model specification. Next, once I observe data, I actually want to make inference about these hidden causes. So what are the most likely causes to have generated that data? And again, because we're in a statistical setting, we're not satisfied with just a single answer, like the conversion rate is going to be 0.5%. Here, we also want a distribution of possible values. So it could be between 0.2 and 0.6%, but which of those values exactly, I can't say, because I only have observed limited amounts of data. So in that distribution that formalizes this is called the posterior distribution. And that posterior distribution, another way to think of that is just as my belief in these underlying causes in the conversion rate. So we start with some initial belief without having seen the data, my priors. Then I observe data, I learn something about the world, I update my knowledge into my posterior distribution. Once I have these posterior distributions, I can do statistics on them, like saying, okay, which of those has the higher probability, or what is the probability rather, that one is better than the other. And that will tell you, okay, now with a 98% probability, the second version of your website is going to be better. So immediately you know what is happening, and you can also then say maybe it's still not high enough, so I want to observe more data. Then you update your posteriors again, and then it's at 99%. So then you say, okay, now we're going to deploy. So that is how the whole problem is structured. The difficulty that I haven't said is in this updating process, going from converting my priors into posteriors by observing data, that is what Bayes formula is doing. And Bayes formula is amazing. It's actually a very simple result, but it is a very elegant formula and looks very simple. But then when you actually try and do the math of that, you very quickly run into problems for even like fairly simple models. And that is what has held Bayesian statistics back for a really long time as well. We have this great framework, but we can't use it because once we start using it, we get these nasty multidimensional integrals over infinities, and we just can't solve them. So luckily, there have been all kinds of approximation inference algorithms being developed. And what is especially powerful about them for the purposes of probabilistic programming is that these work largely automatic on whatever model you dream up. So that allows you in a probabilistic programming framework to write your model in code, then hit what I like to call the inference button and just get your posterior approximation. And then maybe you're not totally satisfied with the model. Some aspect of the data is not being modeled correctly. So then you go in, change the model, and without having to like rederive anything in math, you just hit the inference button again and you get your answers. So that is, I think, how I view the benefits and of the approach of probabilistic programming.
And I know that there's sort of this dichotomy in statistics between Bayesian approaches and frequentist approaches. And it sounds like one of the reasons that frequentist approach has sort of gained a larger mind share is because of these issues of being able to effectively compute the probability distributions of the Bayesian model. And it seems that because we now have tools like PIMC3 and other Bayesian statistical algorithms, that it's starting to gain back a bit of interest and sort of popularity in the statistics community. So I'm curious what your experience has been on that front.
Yeah, I think that's definitely true. So I would view frequentist as more like the 20th century statistics, where yes, we had to be able to derive these estimators using math to closed form solutions, and frequentist just was easier in that regard for many cases. While like all the math is like completely correct and it's a solid framework, it is often a framework that is not really well suited for the scientific discovery process. And one of the key reasons is that people think about frequentist statistics in a way that is actually much more compatible with Bayesian statistics. So they think that like a p-value of smaller than 0.05 means that the probability of a false discovery is smaller than 0.05. But that is the Bayesian answer, not the frequentist answer. I don't want to go into too much detail. I encourage listeners to just read up on what actually a p-value means. But it comes with all these problems, like it's very dependent on the exact data generation and data collection process. So it's different if you say, I collected data for 15 days and got 20 subjects, or I collected so much data that had 20 subjects, or all kinds of different ways that give you the same number of data points. But actually it matters for the statistical test what your protocol was. And that just is not very well suited. And now the other aspect I would say where Bayesian statistics really shines is that because frequentist statistics relies on these mathematical derivations, it is building a new model, the model that you actually think your problem is, right? So if it's not a t-test, but something like a t-test, you would need to go back to the drawing board and rederive the formulas. And if you're lucky, then everything checks out. But if not, then you're basically left to your own devices. In Bayesian statistics and with probabilistic programming, you just build whatever model you think is best suited to understand your data. And then just hit the inference button and be on your way. And I definitely see a slow but steady move away from frequentist statistics. Academia in general seems to be slow on the uptake, but I think it's mainly a question of time.
And so now that we've established what probabilistic programming is and some of the differences between Bayesian and frequentist approaches, I'm wondering if you can describe what the PIMC3 project is and what it offers and how you got involved with it.
Sure, yeah. So when I first learned about Bayesian statistics in grad school, we were using, that was at a workshop in Amsterdam with which E.J. Wagenmakers taught, and there we're using WinBugs, which is like a package which was at its time, ahead of its time. But now it's definitely neither of those. So that, like most other packages, required you to like write your model in this domain-specific language which they defined. And because I was already back then an avid Python user, I was looking for a package that was giving that, and that way found PIMC2. And that allowed you to specify models directly in Python code. So that really suited me well. And I started writing for the models I was building in grad school, a library that built on top of that. So just that being possible was just extremely powerful. And that's how I got to know the authors of PIMC2 better, like Chris Fonesbeck and John Salvatier, who was really involved with that. And talking more to John, he talked about these new class of samplers called Hamiltonian Monte Carlo, which I didn't really know anything about. And other packages at that time were just using what's called Metropolis Hastings, which is like a quite easy and general inference algorithm, but it is, it's not great. It often fails and it's quite slow. And these new class of samplers just way better. So we talked about ways of maybe including that in PIMC2, but it just wasn't suited for that, because for these new types of samplers, you really need the gradients of your model. And the package just wasn't designed to handle that. So John, and I think he was the first to really make the connection, found that package Theano, which is the first of its kind to really be a deep learning library where you do all the matrix multiplications to build your neural network model, and then also compute the gradients, which you need because to do your backpropagation and gradient descent to fit the neural network model. And he realized that this particular package was not just that was possible to use that package not just for neural networks, but it was a general computational package where you can implement all kinds of math and then get your derivatives for that. And moreover, it allows you to compile things to C and then run it at machine speed to be really fast. So he realized that you could implement a probabilistic programming framework on top of Theano, and then did a lot of the core work to really do that. And that is what resulted in PIMC3. And then later, Chris and I basically got involved in that and pushed it further. So it is basically the extension of that package. The benefits are that you can write your models in Python and everything stays in Python, and you can interact with your model in Python. And it is really fast because we compile the code to C or the GPU, and it has these next generation samplers, which are just vastly better than anything that came before.
And I know that some of the samplers are things like Markov chain Monte Carlo or variational inference, and the opening line for the project README is actually very packed with some of these very technical terms. So it says, PIMC3 is a Python package for Bayesian statistical modeling and probabilistic machine learning focusing on advanced Markov chain Monte Carlo and variational inference algorithms. So I'm wondering if you can just unpack that a bit and discuss some of the ways that PIMC3 is used in some real-world projects. I know you already mentioned the possibility of being able to use it for being able to establish the statistical significance of things like A/B testing, but I'm wondering if you can just talk through some of the other ways that you have used it or that you've seen it used in other contexts.
Sure, yeah. So that has been really rewarding to see, is like how people really make use of the software. And it's actually not that easy to get a sense of what people use your package for. If they use it and it works, they just don't come back and tell you that like they used it for a really cool purpose and that it worked well for that. In academia, we see that just because of all the papers citing PIMC3. And these come from all kinds of scientific disciplines, like a lot of astronomy stuff, ecology, quant finance, econometrics, biology, zoology, like earthquake stuff. It's like, it's probably one of my favorite papers because like all the other papers are, of course, in my domain where I did my PhD. And so I can read them and understand them, but the people that are citing PIMC3, like I have no idea what is going on there. So it's being used in like all kinds of different areas for all kinds of interesting purposes. And moreover, it's also used in industry. So there are quite a few companies that we know that use it in production in all kinds of different ways to solve all kinds of different problems. really big companies and startups. One common use case, so it's used for all kinds of stuff, but actually one thing that I do see often is A/B tests, interestingly. And finally, we also use it for at Quantopian to make our asset allocation. So just as a word on that, so we what I like to call a crowdsourced hedge fund. So we have a huge community of quants that come to our website and develop trading algorithms to invest in the stock market. And we pick the best of those algorithms and then license them from the author to include into our fund. And part of my job is to select the best ones of those. And PIMC3 is being used in that process as well.
And I know that a lot of the documentation, as I was reading through, is pretty heavy with different references to probability theory and statistical algorithms. And I know that one of the benefits of PIMC3 being in Python is that it helps provide a bit of a more higher level abstraction over some of those approaches. So I'm curious what you have found to be the requisite amount of knowledge of statistical modeling and Bayesian statistics to be able to make effective use of PIMC3.
Right. Yeah. So there's definitely an initial investment that has to be done. So you need to know about probability distributions, just so you know basically what those do and how to set the right priors. Then you need to know about priors and posteriors and how to interpret them and how to do them, a little bit about the model building process, how to do that properly. And then probably quite some Bayesian practitioners would disagree, but I don't think you really need an in-depth knowledge of like the inference algorithms, for example. Like the hope is, and I think we have succeeded to that to some degree, is that you don't really need to know about that. It's just the inference button and you press it, and without really knowing what's happening, it will do something, it will do the right thing and give you the right answers. And that actually works well also because these new type of inference algorithms, Hamiltonian Monte Carlo samplers, when they don't work, they fail in a spectacular way. And that is really easy then to alert the user and say, actually, don't trust these results. Something went really wrong there. And then, unfortunately, it can be quite difficult and require quite some in-depth knowledge to solve those kind of problems. So when the default approach doesn't work, things get more difficult and intricate. But yeah, otherwise you get by with like core knowledge of statistics and probability. And I think, yeah, the best way to get started is probably to pick up a book that introduces these concepts. So there's Bayesian Methods for Hackers, which is a really fun read, which you can find online, and it's ported to PIMC3. So that is a great read. And then Osvaldo Martin has just come out with the second edition of his book, which focuses on PIMC3 and does a great job of introducing everything in a very practical and applied way. So for those types of data scientists, I would definitely recommend that book.
So can you start by just talking through an example project that would use PIMC3 and the overall workflow of setting up the model, some of the syntax, I don't need you to sort of spell it out, but just at a high level, just like the way that the syntax is represented and just the overall workflow of any heuristics that would be useful for figuring out how to set your priors, building the model, any sort of training process that goes on, and then evaluating the outputs.
Sure, yeah. So one particular use case, which was also very educational for me, was building that model for Quantopian to help with our asset allocation. And the problem is actually quite similar to the A/B testing problem, where we have different algorithms and they produce daily returns. So either you increase your returns by 5% on the first day and then maybe 2% down on the next day, or mostly these are much smaller values, but you get the idea. So we have these return series for every single algorithm, and we want to know which one of those has the best performance to risk profile. So there we have the unknown causes, which are, well, what is the mean of that returns distribution? Is it positive or negative or zero? And we have the variance of that. So these are two parameters that we want to estimate here. And the PIMC3 code, that would be 2 lines. So we say, okay, we have the mean that we want to estimate, but don't know, and we place a prior on that. So here I would say, okay, I already know ahead of time that the mean returns of any strategy will be very, very close to zero, right? Just 10% on average every day is absolutely impossible. So it's going to be close to zero. So I would pick a normal distribution that centers things very close to a very narrow range around zero that is plausible given what we've seen. So that's the first line. And then the second line says, okay, now I need a parameter for the variance of those returns. And there, the first thing that I realize is, okay, well, the variance must be positive. So it can't be just a normal distribution because that has also probability mass on zero. So I would choose something like the absolute value of a normal distribution, called a half normal. Or there's other choices that you could make, but those are like some pretty sane starting conditions. And then I would define my likelihood function, which is how my data is distributed. So that's the third line. And that has two input parameters. And here I'm linking it to my unobservable causes. So the mean of that likelihood function is my parameter I defined in the first line, and the variance is the parameter I find in the second line. So that's how how the model links together. And then I pass in the data that I have observed. So that is the daily return series that I have. Now, here I have some interesting choices actually about what kind of likelihood I use or how I think my observed data is distributed. So good default choice here would be a normal distribution, but actually it's a pretty well-known fact that financial return series are not normal, but they have much heavier tails, much higher outliers than a normal distribution would have. So during something like the financial crash in 2008, 2009, you get like 20% all of a sudden of like daily moves, and a normal distribution just doesn't account for that really. So you could use something else like a student t-distribution. Yeah, those are like different choices you would have, but in the model that just changes one line essentially, where you say, well, now I'm using a different likelihood function. So with 3 lines, I've defined my model that tells me what is the expected return and the risk, the variance of that strategy, the volatility. And then I would just run my sampler and get my posterior that tells me, okay, the mean, and then I could take a statistic and ask, okay, what is the probability that the mean return of that strategy is positive? And so that is similar to the model that I built in the first pass. And then I would report that number and say, okay, the probability that that strategy is profitable is, say, 75%. So we're operating here in like very high uncertainty environments. And then that number could be used by the person selecting the strategies to make a more informed decision. And I thought, okay, that's amazing, really cool approach, and but should make our asset allocations much better. But what I found was that number just wasn't used, right? It just like was reported, but people like looked at it in the beginning, but then like just started ignoring it. And the reason is, well, there's several reasons. One is we're pretty bad at incorporating this uncertainty information in our decision-making process. And there are like no easy answers where like it says, 99% and this one has 50%. So obviously you should choose the one that has profitability with 99% probability. So it's all in this gray area. And then you say, well, I have 10 strategies and they have different probabilities ranging from 60 to 75%. Should I use all of them? Should I just use the top 10? Like, these are really difficult questions. And that basically led to people to make the decisions that they made before, which are the decisions that they think that are best, but not really based on evidence or the model output. And the solution that we found, which I think is profound, is pushing the model one step further into the decision-making pipeline. And I find that is often unappreciated. So what you can do once you have your model, rather than just reporting that number, right, that probability output, you can actually generate new data, different scenarios of what the future could look like given your model and what the model has learned on the data. So something that has a very high probability of generating good returns will generate really good looking returns into the future. Something that is in between will generate, sometimes it'll go down, sometimes it'll go up. So you do that for all your strategies. You generate all kinds of different future scenarios, and then you plug those into an optimizer and say, okay, give me the selection of strategies that will maximize my profitability, or rather minimize the risk of getting a terrible loss. But either way, you want to optimize so that you find the best selection of algorithms with the best properties. And now all of a sudden, rather than reporting a number that people didn't look at, now the output is given like all the inputs that are available, this is the best selection and how to weight them of your portfolio allocation problem. So, and that like was what we used then to actually make these decisions. So all of a sudden, like there was no more human in the loop to make these really difficult decisions, making very difficult trade-offs. And that model just worked way better and was actually being used for its intended purpose. So that idea, I think, of not just making a model, and it could even be a machine learning model, but really going the extra mile and not just reporting like, oh yeah, this is an amazing predictor or whatever, and it is that accurate, is not that useful, right? And in the business world, often people don't really care as much about how cool your model is. What they care about is, well, A, does it work? And B, does it make money? So you really need to be successful as a data scientist. You really need to speak their language. And then that allows you to do that, where you can show like this process works way better than what we did before, and we think it'll be 10% more profitable or something like that. So I think that is a really critical tool for data scientists to have impact in actual business processes.
And so can you talk a bit now about how the PIMC3 project itself is actually implemented? I know that it's gone through a few different generations with the going from 1 to 2 and then 2 to 3. And I know that version 4 is in the works, but curious if you can just dig into some of the architecture and some of the ways that it has evolved and some of the things that you're thinking about as you look to the next version.
So PIMC 1, I don't even know what, I think, so basically PIMC 1 was like a pure Python-based implementation of the probability distributions that Chris Fonnesbeck wrote, I think in his PhD or something. And because it was all in Python, it was really, really slow. Then he, with a few other people, started working PIMC 2, where they found that like, well, most of the time is being spent in evaluating these probability distributions, so we should make these as fast as possible. And faster than Python is Fortran. So they wrote all the likelihood functions in Fortran, and that would speed up the model evaluation by a lot. And that was, so it was much faster. But the downside is that now you have this Fortran dependency and linking between Python and Fortran that make things really difficult to hack on and really difficult to compile and ship and take to production. So that was obviously a downside. And then, as I already mentioned, John Salvatierra wrote PIMC3 and used Theano for all of that. And that just made things way easier and also way faster. So our likelihood functions are now again written in Python, but they're using Theano, so they're still being compiled on the fly to run at machine speed. So now, we're back at a pure Python-based code base that is still fast and gives us gradients, all due to Theano. So it's very hackable and much more maintainable, much easier for users to install and contribute to. So that is much better. And PIMC4 basically takes things to the next step forward, in that will be built based on TensorFlow, but with a similar basically setup.
Yeah, that was one of my questions, was going to be asking what would be involved in integrating with some of the other deep learning frameworks that are available now, and whether that would even make sense, because I know that in Theano, one of the main features that you're making use of is its ability to dynamically generate and compile the C functions for speed improvements. So I'm curious if you can talk a bit about some of the benefits that are gained by going with TensorFlow over Theano or any of the other frameworks, and if there's any thought to making it swappable.
Yeah, that's a good question. So Theano is actually a great package. Like, they have been developing this for at least 10 years and worked out a lot of the kinks. It is really, really fast. It has very low Python call overhead, and the code base is quite readable. Unfortunately, they decided to discontinue maintaining it. So it's being phased out, which leaves PIMC3 sort of hanging. We actually took over maintenance of the Theano code base. So at least that way it'll not completely decay. So anything that, any bugs or version incompatibilities as NumPy and other packages move ahead, we will keep it updated so that PIMC3 users will be able to still use it in a modern ecosystem. But nonetheless, it's not great for the future, right? If like your core dependency basically gets dropped. So for a long time, we've been thinking of all kinds of different ways of trying to find a solution. And one of the solutions, and there was actually a pull request for that, is to just take PIMC3, switch out the backend from Theano to that particular one was about TensorFlow, but you could also do it with MXNet or some other deep learning library. And that is a pretty viable approach, but unfortunately, TensorFlow in particular has quite a high Python call overhead. And the way that PIMC3 works is that only the model is written in Theano and compiled down to C. The samplers are still in Python. So every time you evaluate the probability of the model, you eat the Python call overhead. So on the TensorFlow, that just added way more overhead than we had in Theano. So we would have a really big performance impact. Then we talked to various other groups maintaining MXNet and TensorFlow. In particular, the TensorFlow probability guys have been really helpful, and talking a lot with them. In PIMC4 will be built on TensorFlow probability, which is a package that also a team at Google is writing, where they implement basically all the core functionality that you would need in a Bayesian framework. They have all the probability distributions. They have the core components of samplers. Its focus is not on usability. It's on being able to flexibly build all kinds of different models. But yeah, so it was pretty clear that what was needed is a high-level interface to TensorFlow probability. And that is what we're doing with PIMC4. So now basically, after replacing the computational backend from Fortran with Theano, now we can not only have a new backend in TensorFlow, but we also get all the probability distributions and a lot of the inference algorithms already in our core dependency. And we just have to focus on making the best API we can and really focus on usability. And also, Google is generous enough to support us financially. So for example, now we'll have a developer summit in Montreal with some of the Google guys. So that is going quite well. There's a lot still to be done, and the software is in pre-alpha, I would call it. But nonetheless, that approach showed that like with very few lines of code, we could actually get something that was already usable and quite performed as well. So we're quite excited about what the future holds.
And in the process of these rewrites and upgrades to the different backends, have you been trying to maintain API compatibility, or are you more focusing on just being able to move the package forward and take advantage of the different benefits that the backends provide, and then just relying on users to upgrade their implementation to take advantage of whatever new interfaces you're exposing?
Right. So we try to do that. So PIMC3 didn't really care too much about backwards compatibility with PIMC2. And I think the user base expanded by a lot from PIMC2. And also just, people, it was quite easy for people to switch. Now we're much more cognizant of backwards compatibility. Unfortunately, due to quite technical reasons, maintaining the exact same interface was impossible for PIMC4. But it will look quite similar. So there is a different boilerplate code of how you set up your model, but the model definition itself should look almost identical. So the hope is that it will be very easy to port. So you maybe only need to change a couple of lines that set up your model, but then the model itself can remain largely intact. Having said that, there are some nice API fixes that we're also introducing here. So actually, I think the API will be better.
And I know that in the context of particularly deep learning frameworks, but also some of the other machine learning approaches, there's a need for a fairly large amount of data to be able to effectively build models that approach the accuracy that you need. And so I'm curious how that plays out in PIMC3 and using Bayesian approaches as to how it compares in terms of the need for volume of data, labeled data, and just how the overall differences manifest between a probabilistic programming approach versus some of these more unsupervised learning methods where you're just feeding it a lot of data and just tuning the hyperparameters to ensure that you get the desired outputs.
Right. So it's definitely true that all of that flexibility and automaticity that you get from probabilistic programming comes at a cost, and that it is generally much slower than something like machine learning. Like scikit-learn, if you fit a logistic regression, that will be orders of magnitude faster than if you run a similar Bayesian version of that logistic regression in PIMC3, just because they have the inference algorithms particularly tuned to that one particular model, while we are much more toolboxed, where you can build very general models and then it just won't be as fast. So the focus has been mostly on small to medium-sized models and definitely not big data type of data sets. That is definitely a well-recognized problem, and there are different solutions that you can take. So one of them is, rather than sampling, which is most of what I talked about, which gives you a very accurate approximation of your posterior distribution, you can use things like variational inference. And these scale much, much better. So rather than sampling from the posterior distribution, they fit a target distribution to your posterior distribution. So you introduce several assumptions like that your posterior will be normal, and then it's an optimization problem rather than a sampling problem. And that will just work much, much faster and approach speeds like you see if you were to build like a neural network model. But of course, that comes at the cost of like a not as good approximation. Then there's also a lot of work being done in types of the backend. So particular TensorFlow is well suited for very big models. And that is what I hope we'd be able to do with PIMC4. So it's possible that these smaller models will be a bit slower, although there's also a good chance that they'll be quite a bit faster. But definitely in PIMC4, I think it'll be much more feasible to build like really large models and train them really large data sets as well, just because TensorFlow was really built for that, and also make really good use of GPUs or TPUs. And we have seen quite impressive speedups in that regard. So it's a bit too early to say whether there's actually a use case for that. Like a lot of the models that are currently being built are these small to medium-sized models. But the question is like, is that just due to people wanting small to medium-sized models, or just because the computational framework can't handle more? So that'll be really interesting to see and push those boundaries. And there's definitely a good reason to assume that these big models will be very powerful, because with more and more, if your data grows more and more in size, you can estimate more and more aspects of your data and model them accurately. So with few data points, your model needs to be very simple, but as you can scale the data set size, there's so much more you can basically estimate from there, and much more complex models that you could build on top of that.
And with different machine learning frameworks or deep learning approaches, I know that there's occasionally the need to retrain the model from scratch if you start to experience model drift in a production context. And I'm wondering if the same is true of PIMC3, or if because of its Bayesian approach, it's able to evolve alongside the data.
Right. So in principle, that is possible. And Bayes' formula is at the core of that. So as I said, that is just the formula to update your beliefs. So you see some data, you update your beliefs, you see some more data, you update those beliefs again. And each time you only need to incorporate the new data that you have seen, and in addition to what we already know beforehand. And so that would make you think that is very well suited for online learning. Unfortunately, once you go to a sampling approach, those kind of things become more difficult, because there is approximation error that gets introduced. So every time you do that, you introduce some approximation error, and the quality of your inference will decay over time. With variational inference, that is much easier, and sort of online learning, there's more guarantees that you have in that world. So yes, that is definitely a possibility, but it's not quite as straightforward as one would hope.
And in terms of your overall experience of building and maintaining PIMC3, I'm wondering what you have found to be some of the most interesting or unexpected or challenging aspects.
Yeah, so definitely it's not the code. It is around the people. That is definitely the most interesting aspect for me, is building the community, and specifically the developer community has really grown. So we started with just the three of us, and then people would show up randomly on GitHub and submit a pull request here and then never be heard of again, or maybe they submitted a second pull request. And for a long time, that's how we went about, and we received just random contributions from random people from the internet. And then we started, for like those people that were becoming more active, to invite them to become core developers, and sort of keep lowering that bar, just because often that really activates people. So we have an internal Slack channel where people then get invited once they join the development team. And by now we have 8 active people, and we have monthly meetings. So just building that community has been really rewarding and makes the whole thing just much more fun. And that way you get to know really talented developers. And the other thing that also is just really important is to stay on top of what users do. So we started a discourse forum where people can ask questions, and John Pang who's one of the core developers, is really active in answering all kinds of modeling questions that people have there. And that really fosters also the community. The challenges, one of the challenges that I currently think a lot about is what things to say no to and what features not to include. So in the same vein, right? So you want to merge people's pull requests because that gets them excited and to contribute more, but you also don't want to dilute the quality of your code base by merging things that maybe aren't that required. So, and then also you want to go back and actually delete older stuff that people don't really use or that is not the best. And that we started doing a little bit, but I think there's still a lot of cleanup work to be done. And it's also not, of course, not the most prestigious work. So there's less volunteers to do that. So these are sort of the pros and cons of being involved, I think, in an open source in general.
And as you mentioned, the developer community around PIMC3 has grown in recent years, and I know that there are a number of different projects that have been built on top of it. So I'm wondering if there are any that you have found to be particularly interesting or noteworthy, or any other ways that you've seen PIMC3 used that was particularly unexpected or interesting.
Yeah, so that has also been really rewarding, is seeing other people build on top of that. And my favorite packages are definitely Bambi, which is an analog to another package called BRMS, which is built on top of Stan. And what that allows is to build generalized linear models in very succinct syntax. So if you know R, then it has that really nice syntax where I can say, Y is distributed according to like some covariates that you can include, and then you can have interaction terms, and just a very simple language to specify linear models. And because in a Bayesian framework, you want to also place priors, so you have to extend that syntax a little bit, but then also you want to have hierarchical coefficients in your linear model, so you can include those as well. So overall, that is a really powerful package for one of the most commonly used models that people build. Another package that I really am excited about is called PMProfit, and that is a PIMC3 implementation of the profit model coming out of Facebook, which is a time series prediction model. And that is different from like all kinds of other time series models like ARIMA or recurrent neural networks, in that it knows the business calendar. So it knows that Christmas is a particular day and that Monday reoccurs every 7 days. So it has that logic built in, and just works extremely well on these business type of time series, which is something that other haven't done before. And then two other ones that I think are really interesting, which are much more domain focused. One is called Exoplanet, which is for discovering exoplanets outside of our solar system. And I don't know anything about that, but they were basically able to just add a couple of probability distributions that people use in that field and build a package on top of that people then use to detect planets. I mean, how cool is that? And then another package in a similar vein is BEAT, which is Bayesian earthquake analysis tool, I think. So you can use PIMC3 to study earthquakes. So yeah, I just love that kind of stuff.
And in your own use of PIMC3, what have you found to be some of the most useful features, and what are some areas that you think could use some additional improvement, particularly as you're preparing for the next release?
So for me, the biggest thing is that inference button, that you build your model in Python and then just usually don't need to worry. You just call pm.sample. And also now we change it so that you don't have to supply anything else. So it just detects like what type of model it is, what sampler, then it will decide which sampler to use and automatically tune that sample and everything. So you don't have to do anything. You just call pm.sample, and in, I would say, 90% of the cases, it will just work. Now, for those cases where it doesn't work, you can be lucky and it's not that difficult to fix. But if your model has some characteristics which lead to like a really difficult posterior that is very difficult to sample from, that is a really difficult issue then to solve. And that is where we enter the dark magic of model reparameterizations. So, for example, in a hierarchical model, there is, and I've written a blog post about this, there's this very dense area in the posterior where the sampler has a really hard time of getting in and out of. And there's a very simple trick that you can then do to reparameterize the model. So you rewrite the model in a way that still gives rise to the same model as before, but now the geometry of the posterior is different and makes it way easier to sample from. And that is not automated, right? You just have to know to do that, and that is a thing that you can do in the first place. But also you can't always do that. Like, it depends on the data. So these type of issues are just really, really difficult and require expert knowledge of like what can be done and what should be done. And that, I think, is an area ripe for improvement. And Brandon Willard, who's a PIMC3 developer as well, is working on basically a language where you can easily transform these models from one specification to the other. So you could imagine that you write your hierarchical model in the way that is problematic, and automatically it'll get transformed to the version that you can easily sample from. And so then, like, the user wouldn't even have to know about that or care about that. We just do it as well automatically behind the scenes for you and give you the best representation of that model. So that would be incredible, and Brandon is making great progress on that. So I'm really excited about what that will hold. Now, that will probably not be in the upcoming release, maybe not in the one after that, but maybe the one after that.
And are there any other aspects of PIMC3 or probabilistic modeling that we didn't discuss yet that you'd like to cover before we close out the show?
Yeah, so one fun thing that is now happening, I think in the third or fourth year, is Google Summer of Code. So we always participate in that. And people have made great contributions in the past, like the Gaussian process submodule, which is very flexible to build nonlinear models, nonlinear regression type models is one such addition, or like all our variational inference support comes from Google Summer of Code project. So that is just extremely rewarding, and it's great for the students as well. So if someone is interested and in school and wants to participate, I definitely invite that. That's a great way to get involved. Other things that we got in there is approximate Bayesian computation, which are models where if you can't specify a likelihood function, then you can still basically, but you have you can't specify a likelihood function, but you can generate a data from your process. Then you can still run Bayesian inference. So these types of things are getting worked on, and there's just much more to do. So I definitely invite everyone to get involved. For me, it's just been a lot of fun to build that package and meet a lot of really interesting people.
All right. So for anybody who wants to follow along with the work that you're doing, or get involved with PIMC3, or just get in touch, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. And this week, I'm going to choose the Fantastic Beasts movies. So Fantastic Beasts and Where to Find Them, and Crimes of Grindelwald. So they're set in the same universe as Harry Potter, but they take place before all of those books. And it's just a lot of fun, very well written, enjoyable. So definitely worth a watch if you're at all into any of the Harry Potter, or if you just like a good fantasy movie. And so with that, I'll pass it to you, Thomas. Do you have any picks this week?
Yeah. So science fiction, Hyperion by Dan Simmons. It's probably one of my favorite books. And then if you're into meditation at all, check out The Mind Illuminated, which is like a fantastic technical introduction to learning meditation.
Great. I'll have to check those out. Well, thank you very much for taking the time today to join me and talk about PIMC3 and probabilistic modeling and Bayesian statistics. It's been very interesting, and it is an area that I've found fascinating for a while. So thank you for that, and I hope you enjoy the rest of your day.
It was my pleasure. Thanks so much for having me.